Okay. Our next speaker is Rajesh Chintala from South Dakota State University, and his talk today is nitrate reduction and release by biochars produced from fast pyrolysis.
Thank you. Good, thank you. So I have to just tap it. Oh, keys, okay. Oh, okay. It's not using key. Oh. Do I need to? No, it's working.
Do you know when to advance, when the screen doesn't advance?
Try escaping out and start running.
Okay, and then, okay. Oh, okay, thanks.
Sorry about that.
In this study, we used the biochars we got from as a co-products generated during microwave pyrolysis of biomass feedstocks, actually to produce bio-oil. The surface of these biochars have a greater affinity for ions in soil solution. In soil systems, and also able to control their bio-oil availability. So that's what we have, we are seeing in the current literature. So in order to understand the biochar or to develop the biochar as a soil amendment, it is necessary to study the interactions of biochar surfaces with ions in the soil system. So that will help to choose appropriate biochars or to design these biochars to meet certain soil management objectives. So moreover, in Midwestern agriculture, the nitrogen fertilizers are applied routinely to meet the nitrogen requirements of crops. So especially the nitrification is the quickest reaction pathway of this nitrogen source that results the formation of nitrate in the soil systems, which is highly mobile because it's a less affinity to form surface complexes with the soil system. So they undergo either leaching or subject to denitrification. So there has been several sorbent materials existing in present scientific knowledge and findings. There are several mesoporous materials and functionalized non-siliceous and siliceous compounds. Unlike those materials, which are, these biochars are simple and then relatively inexpensive compared to those sorbents which are already in use in either controlling the mobility of ions or removal of, especially in our case, nitrate. So in this context, so this study was designed to determine the potential of these biochars to sorb nitrate ion, and also we actually used it in this study both non-activated and activated biochars, and also to study a little bit about desorption kinetics and how easy to to get the nitrate from the surface. So this is briefly how we produced the biochars in our study. Basically, we used 3 biomass feedstocks: corn store, switchgrass, and Ponderosa pine, and then we used the microwave pyrolysis. The temperature about 650 Celsius, and the residence time is about 18 minutes, and the power we used is 700 watts. So these are the 3 biochars. So these were actually activated through chemical activation using concentrated HCl for these batch experiments. We used to determine the nitrate sorption and desorption. So these are the overall steps in this study. Basically, we produced both non-activated, activated biochars from those 3 biomass feedstocks previously I mentioned, and then we studied a little bit about the surface characterization, and then the conducting a batch experiments to study the nitrate sorption desorption. So this is briefly the physical and chemical characterization of those biochars, both activated and non-activated ones. If you look into the non-activated ones, the biochars coming from corn stores, switchgrass are more alkaline, more soluble salts, like in terms of electrical conductivity, and then higher cation exchange capacity and point of zero net charge, and then volatile organics and total nitrogen compared to the biochar coming from Ponderosa pine wood residue. But whereas the Ponderosa pine wood residue biochars have higher total surface area and also total carbon compared to other biochars from other 2 herbaceous species, corn store and switchgrass. But whereas in a chemical activation actually decreases most of the chemical properties, but the specific surface area is several times. So that's very crucial for this kind of holding the ions and then controlling the mobility. So these are the baseline character FTR spectra to study what are the functional groups on the biochar surface. So just I would like to give you a main thing. The composition of these surface functional groups are similar in case of herbaceous biochars from herbaceous species like corn store and switchgrass compared to the Ponderosa pine wood residue. So you can see the especially in herbaceous biochars is CN stretch and CO double bond stretch and CO single bond stretch and aromatic CH vibrational band. And whereas in Ponderosa pine, it's like it also has CN and CO and then CH aromatic vibrations. So the chemical activation actually reduces the absorbance of this, vibrational absorbance of these functional groups. But maybe that's because of loss of, soluble compounds during washing process. This happened during the chemical activation. So the acid properties of these functional groups are crucial, and also that generates the electrostatic attraction for oppositely charged ions, which is essential for holding these ions. So this is the surface charge of these, especially these are non-activated biochars. Basically, if you look into the, so there are, if there is a change in pH, the surface charge on these biochars also change, especially this cation exchange and anion exchange capacitors showed at opposite trends, nothing really kind of new as the pH changes. But the the surface charge in the biochars from herbaceous species are higher than the Ponderosa pine. Maybe that's because of higher volatile, those functional groups are coming from, in our case, is volatile organics. So those are showing, protonation, deprotonation as the pH changes, and then giving a lot of surface charge potential for these biochars. So this is the overall batch experiment, the details about how the sorption desorption study was conducted. Basically, 5 concentrations of nitrate solutions were used, and then isotherms like Freundlich, Langmuir models were used to fit the equilibrium and sorb concentrations of nitrate for these biochars. And then desorption, we used deionized water as an extractant, and then used 3 nitrate concentrations, and then we fit the kinetic model to see which one is working for the pattern of desorption. So basically, in desorption, we measure the successive concentration of nitrate with the different agitation times, and then using the data to fit that model. So if you look into the sorption isotherms, you can see the effect. So the x-axis has the nitrate concentration at the equilibrium, and then y-axis has how much nitrate is going onto the surface. If you look into those curves, these are Freundlich isotherms, especially in non-activated. So this sorption is mainly influenced by the feedstock type and also the chemical activation, really highly enhanced by the chemical activation. So if you look into the non-activated biochars, you can see higher sorption in terms of corn store, switchgrass compared to the Ponderosa, the same pattern with even chemical activation, even though it's multiplied because of increased surface area. So that's because these the biochars coming from herbaceous species have a higher volatile organics and also high pH, and then base cation concentration too, that helps divalent cation bridging, so more anions coming onto the surface. So this sorption also influenced by the solution pH and also the biochar pH. You can see the feedstock also has influence on the nitrate sorption, and then chemical activation also influences significantly on the sorption, nitrate sorption. You can see the more, as the pH increases, the more the reduction in the sorption in case of activated ones compared to the non-activated ones. So yeah, these are, so as the pH increases, the more hydroxyl ions that may also compete for the surfaces, and also the pH as the biochar changes, the negative potential also increases, so there is some repulsion. So that's why it's not, nitrate is not going onto the surface as pH increases. This is another, it's not a new information, just we have seen how the nitrate sorption influenced by the presence of other multivalent ions like phosphates, like trivalent and divalent sulfates. It's not like surprising, but those ions are suppressing the sorption, reducing the sorption onto the surface. Especially that phenomenon is more predominant in the activated carbons, activated biochars. So this is again the desorption, how influenced by the pH. So here actually there are 4 factors are affecting the desorption: the solution pH and the biochar pH, and then feedstock type, and also the chemical activation influencing the desorption. So in a chemically activated biochars, the desorption magnitude is higher than the non-activated ones, and also as the solution pH or biochar pH increase, there is a higher desorption because of increase of negative charge potential on surfaces, more repulsion, and also feedstock too. So the feedstocks, especially the corn store and switchgrass biochars, easily getting rid of the nitrate compared to the Ponderosa pine. At the same time, the concentration of the solution you treat to those biochars, if you increase. So these are general common observations, even with other sorbents too. But even with the biochar, the similar pattern we observe. And then we fitted this desorption data, measuring nitrate concentrations at different agitation times, and to see how the pattern will be. So it fitted with the first order kinetics. So it's like depending on the concentration on the surface that determines how much is coming onto the into the solution. So you can see higher desorption constants for activated ones compared to non-activated ones. Maybe not that much different, but there is some difference. So with this study, you can say the nitrate, the sorption influenced by the surface area and also surface charge of these biochars. along with the solution pH, and then what are the ions existing in the solution. And also we've seen these biochars may have a potential at higher concentration systems can hold this nitrate for a while, may not, have a potential to reduce the availability for processes of, in the other processes in nitrogen transformations like denitrification, or maybe they may have a reduction effect on mobility of nitrate in the soil systems. So by increasing the residence time. But I observe, I think to complete the desorption, it takes like 50 to 58 minutes of shaking time. So with that, biochars can increase the residence time of, because we know the nitrate is highly mobile, so it may increase the residence time, so that even in a low nitrate systems, it may give some time for plants to sorb, or maybe the persistence effect stay for a longer time available to the plants too. And then chemical activation has a tremendous effect in terms of increasing surface area by, actually it has a catalytic effect on the cleavage of the bond linkages in the carbohydrates like cellulase and hemicellulase that increase the pore volume and ultimately microporosity or surface area. So more ions can go onto the surface. So there's another way of you can modify a biochar surface to design those to hold more ions. I see there's a possibility we can change the surface of the biochar materials. You can use as a feed, like other sorbent materials, like already in use in removal technologies, or immobilizing in terms of immobilizing these anions. The biochar materials can also be, can be used for that purpose, to play with their surface and then to meet certain goals, like in terms of removal or immobilizing, things like that. So I'm done. If you have any questions.
We have time for a couple questions.
How do you determine the surface charge?
That's a good question. So actually what I did is initially I saturated with the potassium chloride, all the biochars, and then I used sodium nitrate to kick out of the potassium chloride, and then measured the potassium for cation exchange capacity and chloride for anion exchange capacity. So I did with the different pH levels. Treated with the KCl, adjust the pH of biochar from maybe 4 to 10 with the HCl or potassium hydroxide, and then I use the sodium nitrate to kick out of the potassium chloride from the surface, and then measure with the potassium and chloride.
So based on that number, did you get a 0?
No. So, but I did a regression to calculate the point of zero net charge.
Oh, so those were part of the same measurement?
Yeah.
Okay.
Yeah, that's a kind of difficult work. So yeah, it took a long time.
If you have already saturated your biochar with potassium chloride and then replace it, do you use like a filtration to simply replace the cations, or do you do densification
Yeah, that's a good question. Centrifugation is so hard to separate the biochar and solution. I think we did filtration.
So you use like a airport system and you do them and a filtration. So until you reach there was no potassium left, doesn't make sense, right?
No, actually we wash it with this alcohol to get rid of excessive potassium chloride. But in our studies, no, we don't know whether we really kick it out of, but we just shaken for some, maybe overnight, and then we measure and consider it as a cation exchange. And it's not like we are not sure about really we kick it out of all the potassium or chloride. Yeah, maybe because we did only overnight shaking. So if you increase the agitation or shaking time, maybe you may get more potassium or chloride out of the, so that varies with the time of shaking and